let's continue with DC motors. All right. So today let's take up types of DC motors. Okay. So types of DC generators we have already seen, right? So types of DC motors is not a new thing. Only we will be interchanging the type of input in case of motor. So in case of motor, electrical power will be the input and mechanical energy will be the output. All right. So let's start with the first motor, that is DC shunt motor. Okay, DC shunt motor. So I'm considering under self-excited, okay, category. So DC shunt motor, I'm considering under self-excited DC motors. All right. So quickly let me cover self-excited DC motors and separately excited DC motor. Now, the meaning of self-excitation is you don't need external power supply to energize the field winding. Instead, the motor kind of exploits something known as residual magnetism, which is present in the field winding itself. All right. So this residual magnetism is basically property of the magnetic material. So the previous operation will leave behind some traces of magnetic flux. So this tiny amount of flux is enough to start the motor operation. All right. So shunt motor, let us take. First, let us take the electrical diagram. The resistance of the armature, let's take it as Re. Okay. Yeah, I was kind of doing the other way around diagram. Okay. All right. So just rewrite. So let me do it in this way. So this is your input, all right. So what is input? Input is electrical, right? So this is plus minus. So that's your input, and you have your shunt field winding. Say resistance of shunt field winding. Let's take RSH, followed by the armature, right? So armature is consisting of the armature resistance Re. Okay, and that is right. M, because we are talking about motor operation, right? So pair of brushes. Okay, and then the currents. IL being the line current. ISH, the field current. And IA is the armature current. All right, and you know that in case of DC motor, there exists a back EMF. So back EMF is due to the rotation of armature. So when the armature rotates in space, it is going to cut the magnetic flux lines of the field winding. So due to which there will be an induced EMF. Hence it is called as the back EMF, because as per Lenz's law, this back EMF is trying to oppose the cause. The cause over here is the supply voltage V. All right. So that's your back EMF, and this is your drop IAR. IAR. Okay, fine. So let us apply first KCL. So at node K, say suppose, let us apply KCL. So what do we get? We get one incoming current and two outgoing currents. So IL is equal to ISH plus IA. All right. And IA, sorry, is the armature current. And ISH, we define ISH as the field current. So field current can be calculated by knowing the voltage across the field winding. So the voltage across the field winding is nothing but the supply voltage V. So ISH can be determined with the ratio V by RSH. Okay, so that's about the current relation. I think I have spoken about this relation. Okay, next let us apply KVL. Okay, let's say I'm going to apply KVL in the second loop, say in clockwise direction. Okay, so apply KVL. So when you apply KVL, what do you get? You get the voltage V across the shunt field, right? It's the same voltage. Okay. So this being the source and the other EMFs being the drops you can consider. All right. So V minus IARA minus EV minus brush contact drop minus armature reaction drop is equal to 0, or V is equal to, that is supply voltage V is equal to the various drops: armature resistance drop, the back EMF, brush contact drop, and armature reaction drop. Okay, so this is the EMF, the voltage equation. So this is the equation for DC motor. All right, DC motor. So what I'm going to do is just to compare the motor equation with the generator equation, let me write down the generator equation as well. So if in case if you had considered the generator operation of this particular machine, you would have got, in place of V, you would have got EG, right? And in place of EB, you would have got V. That's all. Okay. So in case of generator, it is EG is equal to IARA plus V plus VCV plus AR, right? So this is for your generator. Okay, DC generator. Okay. Similarly, in case of current, you would have got, in place of IL, you would have had IA. So IA would have been IL plus ISH. This is for DC generator, and this is for DC motor. Okay, so this way you can, clear your doubts about motor and generator. You see, only one term is going to change. All right. So it generates electricity, hence voltage. It takes electricity, hence voltage. Okay. V is the supply voltage and EG is the generator voltage. So that's about your DC motor, the shunt motor. Okay. So next, let us consider the series motor. Series motor. All right. So series motor, we'll draw the equivalent circle. External voltage V, connected to few turns of series field winding. So the turns are very few for a series motor, but the area of cross section is very large because it has to handle the line current, right? So this is your RSC, and this is your line current IA, and current through the series field winding, let's call it as IAC, and that is then connected to the armature, right? So let us draw the armature resistance as well. Armature. This is a back EMF, EV. Okay, so this is RA, and let us consider the drop IARA. And the current flow through the armature, let's consider IL. Okay. Now, very interesting results you are going to get in case of DC-CD motor. In fact, DC-CD motor is a very important motor in DC motor category. Okay. Now, if you look at the equivalent circuit, you would see that the load current IL is equal to field current ISC is equal to armature current IL. So that means to say load current is equal to field current, and I can also say that field current is equal to armature current. That is one of the very important observations which you can draw from a DC series motor. Okay, so let's write. So you can apply current law. Of course, you don't have any nodes, so straight in, straight out it is going to be. So load current IL is equal to field current ISC is equal to armature current IL. Okay, now let me clear your doubts. IL is equal to load line current. Okay. IL is line current, ISC is field current, and IA is armature current. Armature current. Now, before writing down, okay, all right, this is your current relation, and now let me write the voltage expression. Voltage relation. So for voltage relation, you can use KVL, Kirchhoff's voltage law. So let's apply KVL to determine what is the source voltage V. Okay. So when you apply KVL in the designated path, what are you going to get? Minus to plus V, then minus IL RSC minus IA RA minus DCD minus ARD is equal to 0. So as IL is equal to IA is equal to ISC. So what we can do is take, say for example, IL is equal to IA, because all the three currents are the same. So with which you will get V is equal to IA times RSC plus RA plus BCD plus ARD. So that is your voltage expression. So this is your voltage expression. This is your voltage expression. Right. Pretty easy. Just you have to apply KVL and KCL to write down the current relation as well as the voltage relation. Okay. Now, very, very important discussion. Generally, it is asked in Viva as well as any competitive exam, right? So the question is, can we start a DC series motor on no load? Let me write it in bold. Can we start a DC series motor on no load? What do you mean by no load? No load means no load is put onto motor shaft. No load is put onto motor shaft. Okay. Now, when you say no load, the current drawn by the DC motor is 0, right? So when there is no load, IL is 0. That is, your motor is not going to draw any power from the supply. So if it doesn't draw any power from the supply, then you can say that the load component or the line component of the current is 0. Now, if IL is equal to 0, what happens to ISC? ISC is also 0, right? Because IL is equal to ISC is equal to IA. Okay. So ISC, we defined it as field current. So your ISC, that is the field current, is proportional to flux. Your field current ISC is proportional to flux. So when ISC is 0, your flux boils down to 0. The flux becomes 0. Now, 0 flux what kind of implication it is going to have on the motor speed. Now, you have seen that DC motor back EMF can be given as EB is equal to 5ZNP divided by 60A. All right. Now, um, this is Z, right? P and 68. You can treat it as constant. So that means to say speed is directly proportional to back EMF and inversely proportional to flux. Right. So from the back EMF relation, you can say that speed is directly proportional to back EMF and inversely proportional to flux. Now, we have started this DC series motor on no load, due to which the field current has become zero, due to which the flux also has become zero. Now, if you consider a zero flux, what will happen? Since speed is inversely proportional to flux, when flux is zero, your speed approaches dangerously high speed, theoretically infinite speed. So at infinite speed, what happens? The motor runs at uh, uncontrollable speed. So that can damage the motor itself, or it can even damage, the operator, because at this very high dangerous speed, it can shatter the bearings and the rotating part of the machine can just burst open, and it can damage the surrounding. It can damage the wealth as well as the human operator. So that's the reason, a DC series motor shouldn't be started on no load. Okay. So can we start a DC series motor on no load? So your answer should be no. You cannot take. You cannot start a DC series motor on no load. The reason is already mentioned. Okay. So that is one of the very, very important aspects of DC series motor. Okay, so that's the reason wherever you use DC series motor, DC series motor has excellent, starting torque capability. Hence, it is widely used in, high starting torque requirement cases such as cranes, hoists, etc., etc. So in crane, hoists, etc., etc., there will be kind of cage connected to the motor shaft, right? What you do is you put the material, and the crane simply lifts the material and place it in the desired location. So whether you place the material or not, the crane cage is always connected to the motor shaft. So there will be a kind of dead weight acting on the motor shaft. All right. And you're not supposed to operate the crane without that, cage or that trolley. All right. So that trolley basically is going to act as some kind of load. So due to which there will be some amount of current drawn by the series motor. And when there is current, there will be flux. And as the flux starts increasing, basically the speed starts to drop. All right. So that's about DC series motor. Next, let us go for shunt motors. Okay. What we will do in shunt motors, we will side by side, let us write compound motor. Okay, that is short shunt and long shunt. So DC shunt motor. Sorry, compound. DC compound. DC compound. First one, let us consider long shunt. And second one, let us consider short shunt. All right. So first, let us consider long shunt. Long shunt means the series field is connected first, followed by the shunt field. RSH, RSC, RE, EB, IARA drop, this is ISC, line current IL, field current ISH, armature current. That's all. So that's your long shunt DC generator. So you can apply KCL at node K will give the current relation. So what do you get? IL is equal to ISH plus IA. Also, IA is equal to ISC because your series field winding is connected in series with the armature. So ISC is equal to IA. All right. So that's your KCL. Okay. Next we can write the KVL. So you can treat it as a shunt motor itself. So KCL we have already written. Now let us write KVL in the anti-clockwise path. So voltage which is coming across field winding, we can take it as the source voltage. So it is going to be V, and then minus, it is ISC RSC, because ISC is equal to IA. So what I will do, IA I will write, and then let me write RSC. Then again I have minus IA into RA. So what I will do, I will club the two resistances, because RSC and RA are nothing but two resistances are connected in series. So RSC plus RA. Done. Then the back EMF minus CB, brush contact drop if at all it has any, and armature reaction drop if it is mentioned. Okay, so that's your KVL relation for long shunt. Okay. Now in long shunt, you can have kind of cumulatively compound. You can have a cumulatively compound operation, or you can have differentially compound operation. Just a minute. You can have cumulatively compound operation or differentially compound operation. I think I have told you in case of generator. Once again, I am going to repeat. Okay, I won't take much time. So cumulatively compound operation in the sense, see, you have the flow of ISH, right? So this ISH will produce field, say, phi SH. And the series current ISC will produce its own field, say, phi SC. This is phi SC. So in case of compound motor, what happens is that due to the presence of two fields, you will have two different fluxes or two different magnetic fields. One magnetic field is due to the shunt current, and the second magnetic field is due to the series current. Now, depending upon the winding placement, you can have either accumulation of flux. So let us say phi r being the resultant flux. So under cumulatively compound, your resultant flux is nothing but addition of two fluxes. That is phi SH plus phi SC. On the other hand, in case of differentially compound motor, the resultant flux is basically subtraction of two fluxes. So phi SC difference of phi SH. So that is the difference. Now, somewhere I mentioned in DC generator that why don't we use differentially compound machines in real time? Do we use differentially compound machines in real time? No. The differentially compound operation is possible in lab environment, only in lab environment. Just to draw the plots, that is speed versus torque, current versus torque, etc., you can have a differentially compound operation. But you cannot use this differentially compound operation in real world. The reason is this. Okay, the resultant flux increases, right? So the speed will decrease. On the other hand, in differentially compound operation, when the resultant flux starts to reduce, the speed starts to increase. So your differentially compound motor is of no practical use because it simply reduces the net flux value due to which the speed simply gets increased. All right. So the same explanation holds good for even short shunt generator. Okay, short shunt motor. So second one, short shunt. Okay. So in case of short shunt, this is your supply. The shunt field winding is directly connected across the armature, followed by the series field winding. So shunt field winding is directly connected across the armature. This is RA. This is EB. It is opposing the back here. Load current or line current. This is RSC, RSH, ISH, IA. Right, yeah. This is ISC. So you can observe that IL is equal to ISC, right? IL is equal to ISC. And you can also say that IL is equal to ISH plus IA, right? The line current IL is equal to ISH plus IA. So that's your current relation. And voltage relation, so probably the voltage across RSH, you can take it as some Vx or VSH. VSH. Okay, VSH. And you can apply KVL in this particular loop, say loop 1. So apply KVL to loop 1. So what do we get when we apply KVL to loop 1? Supply voltage V minus ILRSC minus VSH is equal to 0. Or you can say that VSH is equal to V minus ILRSC. Right. And similarly, you can also apply KVL to loop 2 so that you will be able to relate this back EMF with the supply voltage. So when we apply KVL, okay, apply KVL to loop 2, right? So what do we get? The voltage VSH, right? And then drop IRA, and then we have EB, and then brush contact drop and armature reaction drop, which is equal to 0. Okay. So this is your voltage equation, right? So VSH can be substituted from, okay, let's say this is equation 1 and let's say this is equation 2. So what you can do is substitute 1 in 2. So when you substitute 1 in 2, what you get is V minus ILRSC minus IARA minus EV minus BCD minus ERD is equal to 0. Okay. So this is your voltage equation for short shunt motor. Okay. So it is similar to generator. If you have any doubts, you can roll back and you can check the analysis of generator. Okay. So I'll stop it at this point. Okay. So what we have done is we have considered the analysis. So tomorrow, let us take up the characteristics of DC motors as well as problems. Okay. So hopefully in another 2 class, I will be able to complete module 4. With that, you can say that basic electrical syllabus is completed. All right. So let's meet in the next class. Thank you so much.